All right, let's dive right into one of the biggest, most mind-bending questions in all of science. What is quantum mechanics, the most successful theory we've ever come up with, actually trying to tell us about reality itself? For about 100 years now, physicists have been wrestling with its completely bizarre implications. And the answers they're finding? Well, they're starting to redefine our entire place in the universe. So let's start with a question that, on the surface, seems almost silly. Is reality the same for everyone? Do you and I and everyone else witness the same objective world? I mean, our gut feeling, our everyday intuition, just screams, of course it is. But as we are about to find out, quantum mechanics throws a massive wrench into that very idea. So our investigation is going to start with a really deep paradox. It's a thought experiment that takes the weird rules of quantum theory and shows how they basically put a crack in the very idea of a single shared reality that we can all agree on. And this brings us to the famous Wigner's friend paradox. So picture this. You've got a scientist, let's call her Jimena, and she's in a totally sealed-off lab. Inside, she measures the quantum state of an atom. For her, right there in the lab, the atom just snaps into a definite state. We'll say spin up. She knows the result. It's a fact for her. But for her colleague, Wigner, who's standing outside the lab, the story's totally different. Since he's completely isolated from what's going on inside, quantum theory forces him to describe the entire lab, that includes Jimena and her atom, as being in this fuzzy, undefined superposition of every possible outcome. Just stop and think about what that means for a second. Inside the lab, reality is a known, definite thing. Outside the lab, reality is this cloud of possibilities. You have the exact same theory, but from two different points of view, it gives you two completely contradictory pictures of what is real. This is the crack in reality that we really need to dig into. Okay, so how on earth did we get here? This paradox isn't just some philosophical game. Nope. It is built on decades of real, baffling, experimental results. These are the clues that have forced physicists to even consider this strange, observer-dependent world. The first, and maybe the most important clue, is this idea of superposition. Before you actually measure a quantum particle, it's not in one state or another. It's kind of in a mix of all of them at the same time. You can think of it like a spinning coin that's both heads and tails at once, and it only picks one when it finally lands, when you measure. And you see this perfectly in the famous double-slit experiment. When we just fire atoms at the slits and don't look, they behave like waves. Each one seems to go through both slits at the same time and create this complex wave pattern on the other side. But, and this is the kicker, the moment we put a little detector there to see which slit they go through, poof, they suddenly snap into behaving like normal little particles. The very act of looking, of observing, fundamentally changes what happens. And this isn't some new idea. Werner Heisenberg, one of the guys who founded quantum mechanics, he got this way back in the 1930s. What he's saying here is that you can't separate us, the observers, from the reality we think we're just passively watching. The kind of questions we ask the universe actually shapes the answers we get back. Now, clue number 2 is entanglement. You've probably heard of it. Einstein famously called it spooky action at a distance. Basically, you can link up two particles so that if you measure something about one of them, you instantly know the same thing about the other one, even if it's on the other side of the galaxy. It's a connection that just totally defies our normal ideas about how the world should work. Now, for a long time, physicists like Einstein thought, okay, there must be some secret instructions, some hidden variables, telling these particles what to do ahead of time. But a whole series of incredibly clever experiments called Bell tests proved that's just not true. The properties literally do not exist until you measure them. The physicist Asher Perez put it just perfectly. Unperformed experiments have no results. So all these clues, superposition, the fact that observation changes reality, this spooky entanglement, they've led a new generation of physicists to a really radical conclusion. Maybe, to solve that Wigner's friend paradox, we don't need to fix quantum mechanics. Maybe what we really need to fix is our definition of reality itself. So first up, we've got Carlo Rovelli and his theory, relational quantum mechanics. Rovelli basically argues there is no single, absolute, God's eye view of the universe. It just doesn't exist. Instead, the properties of anything only exist in relation to something else. So for Jimena, inside the lab, the atom's spin is real relative to her. But for Wigner, outside, her state is undefined relative to him. An event is only real from a specific point of view. And then you've got Chris Fuchs, who's the main champion of a theory called QBism. For Fuchs, a quantum state isn't a property of the world at all. It's a reflection of an observer's personal, subjective belief about the world. It's a tool that helps you place smart bets on what you're going to see next. That fuzzy superposition that Wigner sees, that's not the lab's reality. It's just a perfect description of Wigner's own uncertainty. Or, as he puts it, it's a state of mind. So for Ravelli, reality is this huge network of different perspectives. What's true for Wigner isn't automatically true for his friend, because they have a different relationship to the experiment. For Fuchs, it's even more personal. Quantum theory is like a user's manual for you, an agent, trying to make your way through the world. But either way, both of these theories solve the paradox by just throwing out the idea of a single objective reality that exists without us. Okay, so while these two ideas are sort of allies in this fight against objective reality, their creators have a friendly but really fundamental disagreement, and it all boils down to one simple question: who or what actually gets to count as an observer? There's this great story about the two of them in a garden on the very island where quantum mechanics was born, and they're arguing about a stone. Ravelli insisted that even the stone could be an observer, because it has a physical relationship with the world. You know, a shadow is cast on it, that sort of thing. But Fuchs just said that's preposterous. For him, an observer has to be an agent, something that can hold beliefs and use quantum mechanics to make bets about the future. A stone can't do that, and that really gets to the heart of it. Does reality pop into existence from any physical interaction, like Ravelli thinks? Or does it need an active, thinking agent who's using information, like Fuchs argues? This is the line in the sand that separates their two really revolutionary views of the world. Now, you might be thinking, this all sounds pretty wild, like some fringe theory. But these ideas are gaining some serious ground. A recent poll in the journal Nature found that over a fifth of physicists now actually favor these kinds of relational, information-based theories. And what's really crucial is that support is way higher among the new generation of researchers. Something is definitely shifting. So why does any of this matter to us, really? Because these theories don't just solve some abstract physics paradox. They fundamentally change how we see ourselves and our place in the cosmos. In a weird way, they put us back in the center of the story.
So physicists have cooked up even more complex versions of the Wigner's friend experiment. And they've led people like Eric Cavalcanti to an even more shocking conclusion. To avoid any contradictions, it's not just that unperformed experiments have no results. It turns out that even performed measurements don't have absolute universal results. Your measurement is a fact for you, but it isn't necessarily a fact for everybody else.
This puts physicists in a really tight spot. They're faced with a stark choice. To make the math work, you either have to throw out Einstein's core principle that nothing can travel faster than light, or you have to throw out the idea of objective, absolute facts. And when they're faced with that choice, a growing number of physicists are actually choosing to sacrifice objective reality. You know, for centuries, the goal of science has been to remove us from the picture, right? To find a description of the universe that works without us. But as the physicist Marcus Mueller says, quantum theory is telling us the exact opposite. We are not just passive onlookers. We are essential participants in the universe we experience. And Chris Fuchs, he takes this idea to a really personal and beautiful place. If our actions, our observations, our very beliefs are part of what shapes reality, well, then what we do really matters. It suggests we live in a participatory universe, one where our choices have a real creative impact. And as he says, that's an idea that can make life feel truly worth living. So I'll just leave you with this thought. If the universe isn't just something we're passively watching, but something we are actively helping to bring into existence through our every interaction with it, then what kind of world are you creating right now?